So if you grab the note from my website, you'll notice there's only one example for today's lesson, and there's no you tries. That probably makes several of you quite happy. This one, again, we're doing applications, but this time we're looking at applications of polynomials, so a higher degree than just 2. So there really isn't a straightforward way to solve some of these problems. Alright, so we're going to start with marking the text. I left the right-hand column blank this time because there's a lot of stuff on this page. But remember the steps. The first thing that we need to do is number each sentence. In this case, we only have one, so I'm going to skip that step. Next, we're going to circle any key terms. In real life, you will get tons of information and you will have to sort through what's important and what really isn't necessary in order to solve the problem. A lot of math word problems give you only the information you need, so it's not exactly fit to real life situations. So one thing to get, hopefully, practice and get better at is figuring out what information is actually important and how you can use that information to put it together to solve the problem or answer the question. Alright, so we have a box made from a square of material. Notice it says an open box, so we know that there won't be a top to it. That's actually kind of an important piece of information. So even though it's not going to help us set up any sort of an equation, it will help us figure out what's going on with this square piece of material and the fact that we don't have to fold anything over to create the top. Alright, 36 inches on a side. Of course, that's going to be important information. That'll help us to figure out some parameters for the x value, which we're going to get to in a minute. So what we're doing is we're cutting equal squares with sides of length x from the corners and turning up the sides. So I'm going to circle this equal squares because that's important to know that all of these are the same length. So imagine taking this square piece of material, I know it looks kind of rectangular, cutting out 4 corners. So this piece will be gone, this will be gone, this corner will be gone, and if my mouse will move, this corner will be gone. And then these sides right here, this side, this one, this side, and this side that are left, we're going to fold it up to create this box like this. And again, remember it's open, so we don't have a top. Underline any verbal. The next step is to underline any verbal phrases. So I'm looking at this whole sentence and I really don't see anything that is going to lead me to set up the equation. By verbal phrases, again, if you think back to the variation problems that we took a look at, it literally put into words what you needed to translate into a math equation. And in this case, we don't have that. And then finally box the question, but because we've got parts A, B, C, the question is further down, or we've got different questions that we're taking a look at. So the first question is to write a model for the volume of the box. Now remember, when we're looking at a rectangular prism, volume is going to be length times width times height. So what we need to figure out is what are the length, the width, and the height of this box. Well, when we look at this flat piece, what we have to figure out is cutting out these squares and then folding it up. This piece is going to give us our height because all of those sides are going to be folded up. And because we took equal squares out of each corner, all of these heights are equal to x. The length and the width will be the dimensions of the bottom. This piece that's left inside is the bottom, so we need to figure out the length and the width. So I've got this sort of set up for us. We know that the original square was 36 inches, and we cut out or subtracted 2 x's from each side. So what's left is the 36 minus the 2 x's. Same thing here. The length was 36. We knew it was a square, and we cut out or took off 2 x's. So this will be the same piece or the same dimensions, 36 minus 2x. So if you think this is 36 minus 2x, and the fact that it's a rectangle, we know that this piece is as well as this piece, and these are the dimensions of the base of our rectangular prism. So length equals width equals 36 minus 2x. So here, writing a model for the volume of the box as a function of x, I'm going to write V for volume of x equals length times width times height. I'm going to leave it like this for now. Part B, what is the maximum value of x? Use that information to determine the domain. So going back up, when we look at our model here, we've got the side length is 36 minus 2x. In theory, x could be any value, but knowing that we're creating a box, obviously this side can't be 0 or negative. So that gives us a constraint on that x value. And the way I'm going to write that constraint is by saying that 36 minus 2x has to be greater than 0. And then we're going to solve this, and that'll give us part of our domain. So I'm going to add 2x to both sides. Remember, with inequalities, if you choose to subtract 36 and then you divide by a negative, you flip the inequality symbol when you divide by a negative. The fact that I added the 2x over, now I don't have a negative that I'm dividing by, so I don't have to worry about that piece. So we know x needs to be less than 18, but we are cutting some value out. Obviously x can't be negative, that would be adding material to the box, and that doesn't make sense. So our domain is that x needs to be greater than 0, but less than 18. So I flipped this around, that's why my inequality symbol flipped. And then the maximum volume, and at what x value does it occur? So what I'm going to do here is, there's a couple of different ways we can do this. We can use a table of values, because this is going to end up, when we put our equation into standard form, it's a cubic function. If we look at our function, right here, we're going to end up with x times x times x. A cubic function doesn't have an absolute maximum like a quadratic function does. So on this video, I'm going to show you how to find the maximum volume with a table of values. So I'm going to rewrite our function here so we can take a look at it. And I'm going to simplify it a little bit. We had two sides of 36 minus 2x. So I'm going to put that as the quantity squared times x. So setting up a table of values, we know x needs to be bigger than 0 and smaller than 18. So I could do a table of values from 1 through 18 and try and find the maximum that way. But I am going to start with a x value of 4, because I figure cutting out a tiny little edge, it's going to have a very small height, so that probably won't end up maximizing the volume. And I am going to go up from there, and we'll see how far we need to go in order to find a maximum volume. We may need to do more than this, or we may find the maximum somewhere within one of these values. So I'm substituting these into the function. So I'm evaluating v at 4, which will be putting 4 in for both x's. So I'm going to have 36 minus 2 times 4 is 8, quantity squared times 4. That gave me a volume of 3136. When I evaluated v of 5, substituting 5 in for x, I got a volume of 3380. This is a good sign that the volume is going up. I didn't already pass the maximum value of x, so it was okay for me to start at 4. Evaluating v of 6, I got a volume of 3,456. Evaluating v of 7, I got a volume of 3,388. So what happened from here to here is the volume decreased. So an x value of 6 gave us the maximum volume. So to answer the question, what is the maximum volume? The maximum volume is 3,456, and actually I shouldn't have put my equal sign just yet, cubic inches. So I'm going to label that answer as the max volume. And at what x value does it occur? At 6 inches.